Alright, what I'd like to do tonight is just talk through a couple of problems with you dealing with Bernoulli's equation, Bernoulli's principle. So what we're going to do is just go through 3 different examples. Hopefully we'll be able to fit them all into this 15-minute video, and we'll just look at a couple of different instances when we would use Bernoulli's. Alright, so the very first problem we're going to be looking at is this one with the water flowing through a pipe. We're given the volumetric flow rate, okay? So that's the volume over the time, right? Volume over the time then is 80 liters per second. Okay, now the one that we're familiar with using is actually area times velocity, right? That's the one that's given to you on the AP exam, is that the initial area times the initial velocity is equal to the final area times the final velocity. And so we want to get this in terms of that area times velocity so that we can find the velocity. Now in reality it's already in terms of that. If you'll remember, this area times velocity actually was derived from the mass flow rate, right? And the mass flow rate was actually the density times the area times the velocity. And we said that was equal to the density times the area times the velocity. And what we did was we actually canceled out the density since it was the same on both sides. But what happens when you take mass and divide it by density? What do you get? Well, we all know that density is mass divided by volume. And so if you think through that and you write out the equation and solve it, that means that mass divided by density is volume. So if we take the mass flow rate and we divide out the density, what we get is the volume flow rate. So essentially, A times V is the same thing as volume over time. Now that works because it's an incompressible fluid and we're assuming that the densities are not changing. And so the mass flow rate and the volumetric flow rate are both conserved. Okay, so in this problem we're just going to say that the area times the initial velocity is going to be equal to the volumetric flow rate, which we know is 80 liters per second. We can also find the initial area right here because we know that it's 16 centimeters. And so we know that area is pi r squared. And so it's going to be pi times the radius, which is 0.16. I'm putting it in meters. Pi r squared times the velocity is going to be equal to v over t, which was 80 liters per second. Now again, I want it to be in SI, and so I'm going to convert those liters to meters. There are 1,000 liters in 1 meter cubed, and so that means I'm going to divide by 1,000, so I'm going to have 0.080 meters cubed per second. That way all my units are in the right thing. So we'll go ahead and take that. We'll take the 0.08, we'll divide by pi, and then we'll divide by 0.16 squared, and that will give us the velocity, which is 0.99 meters per second. So that is the velocity at 0.1 at the very beginning. All right, now part B says what is the velocity at point 2? So that's up here. So at point 2, we've got that the area is changing. We have that equation that we were talking about earlier with the areas and the velocities. And so again, we're going to take, that was part A, now we'll go on to B. So we're going to take the initial area times the initial velocity and say that will be equal to the final velocity, final area times the final velocity. So that will be pi times 1/6 squared times the velocity, which was 0.995, right, equals the area, which is 8 centimeters. So that's pi times 0.08 squared times the final velocity. And so from there we should be able to solve. So we'll go pi times 0.16 squared times essentially that answer right there, right? Then we'll divide by pi and then divide by 0.08 squared. And we get 3.98. Alright, so velocity at 2 is 3.98 meters per second. Alright, so now we've got 1. We've got B. Now we're looking for C, the pressure at point 2. So what is the pressure up here? Well, it tells us the pressure at point 1. Okay, so now that we know we have velocities, we've got pressures, we know we're going to be using Bernoulli's. So let's do initial pressure plus rho dy plus 1/2 rho v squared. Now this is all initial, right? Is equal to the pressure plus rho gy final plus 1/2 rho v squared final, or at 2. Okay, now the initial pressure is 180 kilopascals, so 180,000 plus the density. Now this is water, so water is 1,000 kilograms per meter cubed times 9.81 times the initial height, which we're going to say is 0 because that's my lowest point, so that term will actually go away, plus 1/2 times the density times the initial velocity squared, which was that 0.99. Okay, and that will be equal to the final pressure, which is what we're looking for, plus the density times gravity times the final height, which it tells us here is 2 meters, plus 1/2 times the density, which is 1,000, times the final velocity, which was that 3.98 squared. So let's go ahead and type that in. So we'll take the left side here, and we'll take 180,000. We will add 1/2 times 1,000 times 0.99 squared. And then we're going to take these other things and subtract them to the other side. So minus 1,000 times 9.81 times 2. And then also minus this 1/2 times 1,000 times 3.98 squared. And we get 152,949, which is approximately 153 kilopascals. And that is the final pressure. So there you go. There's example number 1, down the drain. Let's move on to another one. Let's look at example number 2. All right. Here we go. Example number 2. A nearsighted sheriff fires at a cattle rustler with his trusty 6-shooter. Fortunately for the cattle rustler, the bullet misses him and penetrates the town water tank and causes a leak. If the top of the tank is open to the atmosphere, determine the speed at which the water leaves the hole when the water level is 0.5 meters above the hole. All right, so the water level is 0.5 meters. This height is 0.5 meters. All right, and then from there it's asking us to find the speed at which the water leaves. All right, so I don't know about you, but this looks like a Bernoulli's problem to me. I got pressures, I'm looking for velocities, okay? So let's go ahead and let's calculate how fast it leaves, okay? So we'll start with Bernoulli's equation, which is P1 plus rho v y plus 1/2 rho v squared. Okay, that's all position 1 is equal to pressure 2 plus rho gy 2 plus 1/2 rho v squared 2. All right, so now let's go ahead and put in what we know. I'm going to say the ambient pressure, that's the air pressure. I know that I'm going to have ambient pressure over here, the air pressure over here because the tank is open. And I'm also going to have pressure over here. Okay, so I am actually going to consider that both of these are going to cancel out, right? The pressure, overall pressure outside here, and the overall pressure outside here will be the same, with the exception of the height, which is going to be taken into consideration here, and then the velocity. Okay, so let's go ahead. At position 1, we've got some height. Okay, so that would be right here. We have some height that's above my water, and so we're going to say, all right, the density of the water is 1,000 times 9.81 times y, which is 0.5 meters. Okay, now we talked about in class how if we have a large container, then we can assume that the velocity that place where it's a large container is essentially 0. And so right here on this side of the hole, where the height is 0.5, we consider that velocity to be 0, and so that term is going to go away. Really all we have then is the pressure due to the height of the water. Okay? Now we'll move over to the other side. Okay? When the water comes out, right here, as it leaves the tank, it doesn't have any water pressure on top of it, which means this is going to be 0. Okay? So once we have that, then we'll say, okay, now it's 1/2 rho v squared. So 1/2 times 1,000 times the velocity squared. And so we should be able to solve it from there. If we want to simplify things, cancel out the 1,000. 1/2 cancels out on either side, so 9.81 equals v squared. So let's take the square root of 9.81, and we get 3.13. So the velocity is 3.13 meters per second. All right? Now keep in mind, we made some assumptions there, right? We said that we were counting the position right before the water left the tank. That was 0.1. And then 0.2 right here after it left the tank. Okay? And so those were the considerations we were taking. All right? We said that the pressure, the overall ambient pressure out here and out here was the same. That's why the two pressures canceled out. Okay? We said that at this point, there's water above it, meaning that there's going to be some height there. Okay? We also said that since it's in a big tank, the velocity there was going to be 0. Okay, now as it leaves the tank, it's going to have some velocity, but it no longer has water on top of it, causing this term right here, right? That term is caused by having other fluids on top of it. And so therefore, we've already considered the ambient pressure. It no longer has water on top of it. Therefore, the only thing left is the velocity. And so we can then calculate that the velocity is equal to 3.13 meters per second. All right. Now, part B actually asks if the head of the castle wrestler is 3 meters below the level of the hole in the tank, where must he stand to get doused with water? So if we say that it's 3 meters from there to the man's head, okay, then we're going to have to use kinematics, right? First, we need to find out how much time it takes it to drop 3 meters, and then we can use our velocity to find out how far away it needs to be. All right, so we know that it's going to have a displacement of -3 meters. Vertically, that's going to be an acceleration of -9.81 meters per second squared. And then also, vertically, it's coming out horizontally, which means vertically the initial velocity is 0. So we want to solve for time. All right? So the equation that we will use is x equals v naught t plus 1/2 at squared. All right, so this term goes away because the initial vertical velocity is 0, so it'll be 1/2 at squared equals 3, so 3 equals 1/2 times, that's -3 and -9.81 t squared. So let's take -3, divide by 1/2, divide by -9.81, and then take the square root. It looks like I forgot the 1 on my 9.8. That's all right. So 7.78 seconds. So t equals 0.78 seconds. So if it takes the water 0.78 seconds to fall that 3 meters, and it's traveling 3.3 meters per second, then he needs to be standing approximately 2.45 meters away. So velocity times time equals the distance. This is on the horizontal component, 3.13 times 0.78 equals the answer that we got, which was 2.45 meters. All right, so that's the answer to part B. Hope that makes sense.